Righto, I think I might make a video on how to put these things together for a couple of reasons. Number one, I think it might just be cool to watch. Number two, because this is such a long-term project, like I make one of these about every 6 months or 3 months, I often forget the little details about how to put them together, like how to do the soldering or how to measure the layers and all this stuff. So I think putting the video together might be useful. So this is a completed one. It's not my best specimen, and it's not 100% complete, but this is the only one I've made so far that's got the new PCB inside. So I've got all the bits laid out here to put together. So number one is the PCB. So these are from JLC. I've got a batch of 10 here that just arrived today. Not very much to them. They cost, I don't know, this batch of 10 was about 30 Australian delivered with a coupon or something. It's kind of muddy, so these don't cost very much. And next up we have the super caps. These do cost a little bit. These are about $7 a piece, which is why I'm sad that I put this one in reverse polarity and ruined it along with that one. But you need 2 of these for this type of blinker. These are ordered off Mouser. And so I ordered them in a batch of about 20, and at that scale they cost about $6 to $8 a piece, depending on price, availability and fluctuation and stuff like that. So these are 35 farad 3 volt supercapacitor. Next up we have the solar cells. So these come in a 125 by 125 cell square. These are monocrystalline. I got these off AliExpress. I ordered a batch of 10 of them. There's in 10 of these cells, and from a place called Vico Cell, or that just might be the brand or the manufacturer, not necessarily the seller, but whatever. They are quite thin, you can see, 160 micrometers, so they're very, very fragile. There is a little bit of wastage when cutting them up. Sometimes they crack and you just got to chuck them away. Sometimes you solder them together and they crack and you got to chuck them away. But one of these is generally enough solder cell, enough sort of coverage to make, if everything goes perfectly, 4 blinkers. I haven't been able to find this exact seller again on AliExpress when I tried to order some more. But for 10 of these cells it was about 30 Australian delivered from China, which is not bad. Any monocrystalline cells should do the job, with the caveat that you've got to pay careful attention to the pattern of the stuff on the back. So these have a continuous trace across the back here for soldering the wires on the back of the cell for the positive terminal. You need that continuous trace to solder once it's cut up into these small strips, because some of them have just little patches, little patches as you go along rather than one continuous one, and they're no good, because if you're cutting it up into strips and you have to solder to a part that is just this insulating layer and no solderable surface, then that won't work. The last big part is the epoxy that I'm using to cast them. So I'm using this platinum river table epoxy, not because I'm making river tables, but because this stuff supports deep pours. So it comes in 2 parts, A and B, you mix it 2 to 1. So by deep pours I mean it lets you pour a whole 30 millimeters in one go. Some epoxies generate too much heat for that to be viable, and the expansion and contraction while it's setting ruins it. But the river table stuff tends to be built to be able to pour deep pours, and so it doesn't generate too much heat. It does set a bit more slowly as a result, but it does mean that you can do one little pour to set it up off the bottom and then one big pour to fill it all up. So that's all the bits. Oh well, there's some bits of copper wire and stuff you can see inside there. Solder, flux, that kind of stuff, consumables. But that's the key lot of stuff. Plus the programming stuff you need. Back in a sec. So to program the software, or the firmware, into these boards, you need one of these, or something like it. This is an AVR ISP, and it just plugs into a computer and lets you talk to these little chips. Not to be confused with just a general USB to TTL serial converter. Those are ubiquitous. But I don't know exactly what, but there's something special about the in-system programming interface that these ATtinies use that needs this kind of widget. So it's got a little little Atmel microcontroller in there and some other bells and whistles, and it runs some firmware. I don't exactly know what it does, but it lets you write software into these things. And this thing is an optional extra, but it's got some pogo pins on here. I put this together myself, little pogo pins that lets you just boop, push down onto little pads there and program them up. Makes it a hell of a lot easier to get good contact. But you know, you could get away without this left-hand piece, but you definitely need this right-hand piece or something like it. There's a few different options on the market. This one's open source and cheap, so I went with that one. So the other thing you need is a laser cutter, unfortunately. So to cut up these solar cells, you need to be able to score the cell, and the only way of reliably being able to do that is with a laser cutter. And so let's do that. Right, so we're all set up, almost ready to cut this cell. So we want to do one cut in parallel to those solder strips that you see on the back there. So we're going to cut across here, and that'll give us two strips half as wide that we can then cut up into smaller cells and then assemble them to make our solar panel for the blinker. So I've got light burn running over here, and so you see the magenta square is the 125 by 125 of the solar cell, and then across the center I've got a dark blue line that will cut it in half, and that's 2 passes at 50 millimeters per second at 70% power on an 80 watt CO2 laser cutter. So let's go make that happen. There we go. So it doesn't cut it, but it scores it. And you can see that there's now a sort of inflection in the cell. So that's given us a line along which the solar cell will preferentially snap when we stress it, like so. There we go. So previously, like this surface here is a bit grotty and rough, and I can't imagine it's good for the solar cells to be sitting up against it. I've previously tried doing this process on a flat sheet of plywood. Unfortunately, the air blowing out of the air assist there causes the cells to sort of wibble and wobble and jostle about, which is no bueno for accurate cutting. I did try turning the air assist off, but that changed the parameters of the cut because there wasn't enough heat being removed, and it led to a little bit more thermal cracking, or at least there appeared to be more. I didn't really spend too much time being scientific about it, but in any case, doing it on this grill is the way to go. So next up, we want to rotate this 90 degrees and then set up a job on the laser cutter that just does a single, or 2 passes, zoop zoop, that are a certain distance off the bottom of the x-axis here. And that's to cut the thinner strips that include a section of this solderable strip in the center here. So for this run, I'm going to do some slightly thinner cells than normal. I'm going to try like maybe 8 mil. Previously for my other blinkers I've done 10 or 12, I think, because I want to try to make a smaller blinker, because the solar cells that are in them currently are oversized for what they need. So I'm going to set that up and we'll do those cuts. Okay, so we're set up for another cut here. So we're just going to trim off, I'm going to try 6 millimeters, make a 6 mil strip, and use that to make some smaller cells. So I've got the job all loaded up. Let's give it a shot. Okay, so I'm all set up for the next cut, so I'm going to do a 6 mil slice off the bottom and see how that goes. see our little score. I haven't actually finished. I stopped it too early. My safety monitoring system is a bit knife edge. Okay, so I had time to cool between those two passes, so I'm not particularly hopeful that we'll get a good result here. I can't see any inflection that indicates that it's been thermally shocked. I might run that job again. There we go. So you can see by the sort of play of the laser light there that it's been sort of folded up a little bit, which is what we want to see. Now, as I try to hold my camera between my knees here, bear with me while it wobbles about a bit. That's not good. So give it a little gentle twist. And there we go. One little cell. So you may ask, why don't I cut a bunch of strips off at once? Why do one at a time? And that's because of that inflection, that bend in the cell. Because if I cut, by the time I get up to here, it's sort of curled up like a banana, and that puts the laser out of focus. So I find it best to do one cut at a time and snap it off, and then do it again, and again, and again, and again, and again, and again. Okay, I'll do that now. Okay, so it's all chopped up into 6-ish millimeter width strips. Most of them came out fine, only lost one, which is great sort of yield. A few of them have some crumbly edges. So the downside of this approach is that because this stuff is so thin and so fragile, it's really hard to see the sort of micro fractures that develop sometimes, and they always spread from the edges, especially around little chips and chunks that are popped off, like on those few there. So I've got to go through and carefully inspect all of them to make sure that once I start soldering them together, they're not going to fall apart, because there's little more frustrating than finishing an array of painstakingly soldering a few of these together, and then noticing one in the center has got a crack in it and won't generate much voltage, which is a pain in the butt. But this 6mm strips look to have turned out alright. I was worried that they might be a little bit too thin for the cutting, but it seems to work. So now to assemble them into a panel. The footage I've got to put in here of soldering a panel together is using the slightly wider strips that I've cut up previously. And it's a pain in the bum to film around the camera, so I think I'll just use that footage here. Okay, bye. So here I've got one solder cell sitting on a piece of wood for some insulation, and I'm putting some solder flux on there. That's some Chipquick SMD 291, and I'm using leaded flux core solder here. The wood's there to insulate it, to stop all the heat being wicked away into the glass, because you have to manage the heat quite carefully throughout this process, such that all of the solderable stuff gets fully wetted out. And the other main factor is to keep the working face of the soldering iron parallel to the solder cell. So I'm using a chisel tip here so I can get a good bead of solder on the end of the tip. And then you just wet it out like that. So there's a couple of other important things to keep in mind. The flux can sometimes glue it down to the surface you're working on there, like it did just then, and I sort of snapped off the tip of the solder panel there. Not a huge deal, as long as you don't crack anything too central. The other important factor is that the flux is an acid, and it will damage the solder cells if you leave it on there too long, and it will also tend to dissolve the white stuff you see on top of the solder cells. So that's I don't even know exactly what it is. It's some sort of proprietary magic, but it's some sort of copper / silver / some sort of conductive stuff that they screen print onto the solder cells to make it conductive. If you leave the solder on there too long or let it get too hot, then it will just sort of etch that off, and then you bucket. You just go to throw it in the bin. So I'm soldering at 270 degrees here with a quite chunky tip on the soldering iron. So when I put it down,
it has enough heat in there to instantly wet out and do all the needful. And then yeah, just sort of trim off the stem of the tinned wire and continue on. You hear that little crack just then. Don't know if you heard it, but that's absolutely gut-wrenching when that happens, because it indicates that a microfracture has formed. But this one turned out perfectly well. Happy days. So here we've got two little solar panels soaking in some isopropanol. So this is to soften up the flux so I can clean it off. Often I can just give them a little slushy slush to get off most of it, but sometimes I give them a rub with a little air cleaner to get all of it off. So after they've been in here for a while, hook a multimeter up to them and take them out in the sun to confirm that I'm getting the full 3.2 open circuit volts out of them, and that's just to check that there's no shorts and everything's looking tickety-boo. So yeah, after they've been tested and cleaned, then I solder them on to the blinker PCB and the super caps and everything. Then I dunk it all back in here to clean all the flux off all of that, and then I'll let them sit in the sun for a bit to let all the isopropanol evaporate off, and then cast them in resin. That'll come next. So I've got it all soldered together now. I've had it out in the sun for a little test and to drive off the isopropanol that might have soaked into the super caps. And I've laser cut this little casting mould that's 8mm bigger than the blinker on every dimension. So I'm going to get these pieces waxed and then taped up, and then I'll be able to cast the floor of the mould. Okay. Alright, so I'm all set up, ready to do my pour. So for this one, I'm only going to put an 8mm layer on the bottom there, and based on the size, that means I need about 20 grams of that one and 10 grams of that one. Then I'll pour it in and chuck it in the pot and vacuum the bubbles out. Okay, so buckle up for some left-handed filming. So I've mixed up 20 parts of part A to 10 parts of part B. And I've just got that stirred up. I skipped the stirring because you've probably seen a million videos of people on YouTube wearing black gloves stirring resin, but this bit's fun. Alright, I'll seal off the vacuum pump side of things. Oh, there's a bit of a leak. Oh well. So you see, it didn't froth that much. That's because previously I had the bottles of resin in here, cracked the lid, and degassed the resin prior to mixing, which helps cut down the frothing on this stage. But you see there's a bit of froth on the top there. Then we let the air back in, and a lot of the froth just drops away, which is cool. Okay, let's pour this up. And a bloop. I'm not going to be able to scrape out this cup one-handed, am I? Righto, so I've just degassed this resin. Now it's time to do the final pour. So something I've been going back and forth on is whether I should vacuum it after the pour to get all of the residual bubbles out. So you can see in there, I under-measured the first floor layer. It's only 5mm thick, it's supposed to be 8, but whatever, I'll deal with it. So I've got the blinker assembled in there, it's roughly in the center, close enough. The solar cells are pretty irregular in length, and so and the hand soldered in there, so they're not exactly, so it might look crooked, but you know, it's within a mouse fart of being true to the sides in there. I've also had that out in the sun for a test, so it's all good. So now let's pour in the resin. This is the fun bit. Here we go. Blurg. So the reason I go back and forth on whether I should vacuum it after the pour is on the pro side, it gets out all the bubbles. So you see there's bubbles coming up there. So some of those might be
under the solar panels. So we don't really want that. We want everything to be nice and crisp. Downside, there's air trapped inside those capacitors, so they're not a hermetically sealed component. And when we pump the vacuum down, we also pull the air out from inside the capacitors. And when we release the vacuum, we are then pulling resin into the inside of the capacitors. And I don't think they're meant to handle that. So I've done that, as in I've vacuumed down a couple of the most recent blinkers after doing the pour, and potentially got the capacitors full of resin. But I might skip it for this one, and we'll do a long-term compare on performance. See if those ones cark it earlier because the resin inside the capacitors is a big bad thing. But, you know, on the other hand, it might not be a thing at all. It's hard to say. Don't really have a robust way of testing it. I did run a few tests by vacuuming down some capacitors and then filling them back up with air again and checking whether they still held charge, and they were fine. They endured the vacuum fine, but what I'm uncertain about is whether they endure being filled with resin. I could probably test that by casting some supercaps with the leads poking out. See, there's a big bubble that just came out from underneath the solar panels. So I'm going to do a little tilted tilt to try to give the bubbles a way out. I can't really tilt very far because I'll start pouring the resin out of the mold. But I did also pre-warm this resin to make it a bit runnier, so the bubbles will have an easier time escaping. But yeah, you can see there's a bubble coming up on that left-hand side there. That was previously trapped, and I can see another one under there. Ooh, gotta resist. I've got to resist vacuuming this. I could prop it up on an angle so the bubbles have like an incline to work their way up and out, but then the resin might set at an incline and then I'll get uneven thickness, because I know this pot on this bench is roughly flat. I might prop it up for 10 minutes and then come back and lay it flat again. 10 minutes should be enough to get most of the bubbles out. But that's what it looks like. Okay, bye. And here we have it. It's about, 3 days after I did the pour. And it's mostly hard. As you can see, I had a go at cracking it out and was not successful. So something I've learned time and time again is you should let the resin set. And then, once it's set, it doesn't stick to the acrylic so much. And it is much happier to let go rather than you just sort of stretching the resin away from the body of it. So once the resin's set, you can take the acrylic off relatively straightforwardly. So for this one, I used some like furniture polish wax, just because I had it laying around and already had a sponge stuck in the top, as a mold release. And you can sort of see some of the wax residue there reflected in the light. And I don't really like it, but some of that surface texture is transferred onto the resin there. So some of that will sort of buff out with some light abrasive, but I'm trying to cut down on the number of post-processing steps. Oh. So these ones were already broken. I'm trying to preserve the acrylic so I can reuse the molds. It's a couple dollars, about that worth of acrylic, but still. Oh, I'm going to really destroy my fingernails here, aren't I? Come on, don't crack. Whee! And so on and so forth. So this one's been sitting out in the sun. I don't know if sitting in the sun makes the acrylic set faster. I mean, I would have thought like the UV might have some effect, but I don't know, whatever. I'm not sure if you can see this on camera. Yeah, you can. I'll just need a precise pointer. So you can see here, there's a difference. There's sort of, you can see a refractive effect, just faintly, like two different densities of medium coming together. So this is the first layer that was poured, and this is the second one. So it's interesting, you can see that discontinuity there. I don't know if that'll go away once the resin is completely set, because this stuff would be completely set, but this stuff is still ever so slightly soft. Like you can see, I can sort of dent it with my thumbnail. But once I get all these other bits of acrylic off, then we can run this through the router to round over the edges. And I'll do that now. Okay, here's the router table. Router's down there. I think this is like a 8mm radius round over bit. So basically it's got a bearing on the top, and so I run the bearing along the side of it, and it puts a nice radius all round, such that when this gets dropped it doesn't have this stress concentration as it hits on an edge or a corner. This is the most sonically unpleasant part of this whole process, so I'm going to pop the camera on a clamp and put some hearing protection on. And there we go. So now they're all nicely rounded over. You may have noticed there are a few sort of what would ideally be extraneous cuts there. That's mostly due to the fact that these aren't platonic solids. Like you see, there's quite a lot of variation to the surface texture on that one. Not quite sure why, but it does mean that you have to recut on different angles, because where the cutter cuts is determined by the surface along which the table rests and the bearing on top there. So when those two surfaces aren't exactly perpendicular or regular, then you have to come back and do a couple cuts to close in on perfect. Close in on good enough, I should say, to get what you want. But there we go. So I'll have a bit of a close look at these and see if I can see any damage to the solder cells as a result of the vibration. Not that I could do anything if there were, but just out of interest. I have tried to make silicon molds, so I can mold them with the corner radius built in. But I never really got great results out of these molds for various reasons. But they kind of worked, kind of. Now I've got to bust out the shop vac and clean up all this awful dust. It's like fine flaky stuff that just sticks to everything and gets everywhere. It's horrible. Okay, sweet, that's all done. complete from start to finish, one blinker. So for the ones I'm going to use for geocaching and hang up in a tree, I think I might bore a hole straight through here because there's nothing of import in there, and just drill down straight down through there with the drill press, and then put a stainless steel loop of wire through that and crimp it. I think that'll be pretty good. I've got two solar arrays soaking in the isopropanol right now, and I'm thinking of making one with the solar panel on both sides, such that it can hang from a tree and you don't have to necessarily be too fussed about making sure this faces in the direction of the sun as it sets, because I imagine most people would be out looking for this geocaching blinky signal just at dusk. Okay, bye bye.